Okay, Physics 1101. This will be talking about part 2 of chapter 3, and we'll be dealing with projectile motion. And this will be section 3.5 and section 3.6. And that will be basically what we'll be doing this chapter as far as that is concerned. So what we're going to be looking at is two different types of projectile motion. We're going to be looking for one where we launch from height, launch from certain position, I would say a height, with some speed, velocity v0, and an angle of theta, and it will land at the same position, height-wise. So it's not like kicking a field goal where you have to kick it over a higher post. We're doing the simplification here, and this is the distance that it travels, or the range as we call it. So velocity will be in meters per second. And in this case, and we can use the PhET lab for doing the same sort of thing. If you look at that, is in this case, range is given by the expression. Okay. V0 squared times the sine of 2 theta, so it's twice the angle, over g, where g is, we'll be using a positive value, 9.8 meters per second squared. Right, so that's the equation there. Again, the range is from the distance horizontally to where it lands. So as an example, let's do one here, where, let's say we launch it with a velocity of 20 meters per second and an angle of 15 degrees, right? How far does it actually go? Right, in this case, and for purposes of simplification, I'm going to round g to 10 meters per second squared. I'm going to do this on a calculator. So in this case, what we have is then the range will be v squared, so it'll be 20 squared times the sine of 2 times 15 over 10, which would be 400. The sine of 15, this is actually 30 degrees. Sine of 30 is 0.5 over 10. This would then be 400 times 0.5 is 200 divided, that would be 20 meters. Right, so that would be how far it'll actually go in this case. And we'll look at the PhET simulation to see how this actually does, if we can verify this. So that'll be case there. All right, so keep this in mind. We'll do the PhET simulation as part of the second part of this handout. So that's one expression. That's section 3.6. The other thing we're going to do is with this. So this is the expression you'll be doing. So before I move on, this is the expression. We have v0 squared times the sine of 2 theta, where theta is in degrees, over g. All right, and this will be in meters. All right, so let's move on here. And in this case, the next thing we have for projectile motion will be if we launch something from a certain height, h or y is h, so it's certain, so this will be a certain meters up, and we launch it horizontally with some velocity v naught, what we're going to first of all realize is this will travel in a parabolic path. So we'll travel a distance x as it falls y. And the question will be is based on v naught, how far out will it go? Or likewise, we know x, how fast was it going originally? All right, the way we can do this is with a variety of ways. In this case, we'll give you, say y is 100 meters high. So y is 100 meters. Now we go back to chapter 2, and in this case, why does that make a difference? Well, it turns out the relationship between velocity v and distance is velocity over time. Velocity is distance over time, displacement over time. So in this case, if we're given v naught is x over t, then x will be equal to v naught times t. So if we can solve for t, and we know v naught, then we can solve for x. So in this problem, we're going to be given usually this distance, the height that it is, and either v naught or x, depending on what we're trying to do. So in this case, we're giving v naught, let's say v naught is 10 meters per second. How far out does it actually go? All right. So what do we do here? Well, we got to first of all find how far it's fallen, how long it takes, because once it falls, it's basically in free fall, and it's moving along horizontally at the same time. So we're going to go back to chapter 2, where y is y naught plus v naught t plus 1/2 gt squared for a fallen object. Now for this particular problem, v naught is only in the horizontal direction, so this expression goes to 0. Y in this case is 100 meters. Why not? And g, since we're using this as positive, g will be minus 10 meters per second squared, just to keep things simple. So this would be plus 1/2 times minus 10 times t squared. So this will be y is equal to 100 plus minus 5t squared. Move that over the other side. 5t squared is 100. Divide both sides by 5. We get 20. And so t is approximately 4.4 seconds. All right? So in this case, then, we can find x. You know v naught is that. So x will be 10 meters per second times 4.4 seconds. And that turns out to be 44 meters. So that's the example there, what we've done. So x would be 4. So if it falls 100 meters, it will travel 44 meters horizontally at the same time. All right? So those are the only kind of questions we have. So we'll be using this expression. Generally, y is y naught plus 1/2 gt squared. And then we'll be using this expression, where again, v naught is only in the x direction. So we're either given x or t, but we need to find t first so we can solve for this. All right, so that's chapter 3. I'm going to do a couple simulations. The second part to demonstrate how projectile motion works. I'll click on to the links. Motion. Let's get some of these. So we have, we want projectile motion. Okay, and for this one, we're going to go straight to the lab. And what we have here is projectile motion. We have a cannon, which is fired at height, and we can measure it with a measuring tape. We'll launch it from whatever angle we want. Okay. And then we can measure the tape by how far out it goes. So an example there is 15 meters. So we will then fire the cannon at the angle we have. The angle here in this case is 80 degrees, you can see from here. And we'll fire it, and that's the path it takes. So if you want to do this, again, this is part of the other lab. In this case, the range, you can figure out how far it actually goes, is approximately 11.3 meters. All right, now in the example I did, I had it is 15 degrees. Oh, I'm not sure I can get it down to 15. Well, anyway. Well, we'll do an example here of, and shoot it at 20 meter, shoot it at a velocity of 10 meters per second. And then we fire it, and that's as far as it goes. So okay. Oh, 20 meters per second, that's right. Let's try an example at 20 meters per second at that angle. And in this case, it goes much, much farther. So in this case, we'll go 31.3 meters. Now in the example we had with the problem I did, at 15 degrees, it should only go 20 meters. So that's the case there. Now, interesting thing here is if we look at, this is the angle 25 degrees. If you try doing it at 90 minus 25, which would be 65 degrees, and fire it, and we can see where does it end up going. And it ends up going at exactly the same spot. As far as that, we do another example similar to that. Let's try clearing it. Shoot it at say 30 degrees with velocity of, let's say, 10 meters per second, so we can see it all. Fire, and it goes to there, which turns out to be about 15, looks like 7.15 meters. So we'll do 90 minus 30, which would be 60 degrees. Fire again, lands exactly the same spot. So that's part of what you find is if you do the angle and 90 minus the angle, you'll get the same values for that. What we're not going to do, we could do, let's see, height. Let's see, height, we could raise it up more. We're not going to do that in this case. So we'll leave it there. Okay, so that's the FAT lab on projectile motion, and have a good